So we talked about related rates problems yesterday, and they were pretty basic. We're going to get into some harder related rates problems today. So the first one was on your homework, but there's actually kind of some shortcuts to doing it, and something that is very crucial that you do in AP Calc, which is always change things from degrees to radians. And you'll see why the answer you have on your homework is probably not completely right. All right, so the first thing says two sides of a triangle have lengths of 12 and 15 meters. So like I was saying, that's pretty big. I don't know what would make a triangle with 12 and 15 meters, but we'll go with it. And we kind of mentioned this yesterday. If things are constant, you can plug them into the equation, okay? So these are a constant 12 and 15 meters. Imagine you have like these two sticks, and the two sticks are kind of like getting closer together or getting further apart, so the angle between them is changing. In this case, the angle is changing d theta over dt at a rate of 2 degrees per minute. And that's the thing that I said we're going to have to change into radians, and I'll show you why we have to change it to radians. Okay, so when we come up with the area equation, 1/2 AB times sine of theta, if you do not plug in the constants, like I was telling you, some people at the AP conferences I go to refuse to let their students do this, it would be quite complicated because you would have to do 1/2 AB times sine of theta using the product rule. And then you'd also have to use the product rule for that. So a product rule within the product rule. So if I was going to quickly do this, you don't have to do it, but watch what I would have. I'd have 1/2 AB times the derivative sine of theta is cosine of theta d theta over dt, plus the derivative of 1/2 AB is 1/2 a dB over dt, plus 1/2 dA over dt times b, and then all times sine of theta normal. That's a lot. Like, we don't want to do that. Agree? Yeah, so that's why I get kind of mad when like teachers are always like, oh, I never let my students do that. I'm like, this is doing them a disservice, not teaching them they can do this. All right, so A and B are both constant values. So we can plug in A and B. So I have A is equal to 1/2 12 times 15 times sine of theta, which simplifies down to 90 sine theta. So now when I take the derivative, it's not scary at all. It's just 90 cosine of theta d theta over dt. And we can handle that.
Wait, where did the 90 sine come from?
I did 1/2 times 12 is 6 times 15 is 90. So I just found the number. All right, so if I start to plug things in, so like I could plug in 60 degrees. Cosine of 60 degrees is what? What is cosine of 60 degrees? You all know this. It's 1/2, right? So I can plug in 60 degrees. So what I'm guessing you guys did on your homework, so don't write this, is you probably did cosine of 60 degrees in here, and then you put the d theta over dt was 2 degrees per minute, and you ended up getting, let's see, 1/2 times 2, so 90. So this wasn't exactly the same as your homework because I think you had 3 degrees per minute as your answer. So your answer would be 90, but the units would be wrong, okay? Because for here, 90 came from the 12 and the 15 and the 1/2. Those units are meters squared, right? Cosine of 60 degrees, which is 1/2, is just a number. We call those trig ratios. It's a ratio of like the side lengths. It's just a number in the end, right? And then the degrees per minute is degrees per minute. So this would be 90 meters squared times degrees per minute, which is really weird. We would never write degrees like that, but what unit should I have if I have dA over dt? Meters squared per minute, right? So there's something that is wrong, okay? So every single time in calculus, we never do degrees in calculus. We always do radians, and this is one of the reasons we always do radians, because radians is what we call the non-unit. So when you see something with radians, like 180 degrees is the same as pi radians. Radians is like a name that we made up. It's not like a unit. Like, what's a radian? Like, radians is not like feet or inches or anything like that. It's nothing, okay? Radians is, pretend it's not there. It's just saying 180 degrees equals pi, okay? So when we plug this in, we're going to have dA over dt equals 90. We can do cosine. You can change the 60 to pi over 3 if you want to. In that case, it was fine if you did 60 because cosine of 60 degrees is still just going to be 1/2. But then right here where I have d theta over dt, I have to change it. So d theta over dt is 2 degrees per minute, but we need to change it so we have 180 degrees on the bottom, pi on top, so it becomes pi over 90. And my units are per minute, like 1/minute, or radians per minute, right? Do you guys see that? So it's going to be pi over 90 here. So 90 times 1/2 times pi over 90. So we end up getting pi over 2. And now our units are what we want, meters squared per minute. Okay, so it's kind of weird, but basically if you see that you have degrees in a problem, I would just change them to radians. That's the best way to do the problems. All right, so the next problem. So it says a balloon rises at a rate of 3 meters per second from a point on the ground that's 30 meters from an observer. So here's my observer, and the balloon is rising. I don't know how to draw what kind of balloon it is, hot air balloon, whatever. Find the rate of change of the angle of elevation of the balloon. So I'm finding the rate of change of this angle right here, theta, when the balloon is 30 meters above the ground. So the balloon is changing, so this is y, and y is getting bigger. So dy over dt, we know, that's the 3 meters per second. That was here. So it rises at a rate of 3 meters per second. All right, can we set up an equation that relates y, theta, and 30 if we need it? Yeah. What equation are we going to use? Yeah, exactly. So we're going to say tangent of theta equals opposite, which is y, over adjacent, which is 30. So you can take the derivative here, or you can like multiply the 30 over. So 30 tangent theta equals y. And then take the derivative. So we get 30 secant squared theta d theta over dt equals dy over dt when we take the derivative. So remember, whatever variable you had, tack on the d theta over dt, dy over dt, whatever it was. Okay. So sometimes we need to use a second triangle because we don't know what theta is at that point in time. Can you guys guess what theta is at this point in time? You should know this. It's 45 degrees. So we need that for right here, for the theta. So we can find that by using the original equation. Tangent of theta equals 30 over 30. Theta is equal to 45 degrees, which we're going to write in radians, pi over 4. Just because in calculus we always use radians, right? We talked about that. So we're going to do 30 times secant is 1 over cosine, so cosine was root 2 over 2 squared. D theta over dt is what we're trying to find, and dy over dt, it's rising at a rate of 3 meters per second. Right? And we just solve it out. So if I do root 2 over 2 and I square it, so what is root 2 over 2 squared? 2 over 4, which is 1/2. So if I have 1 over 1/2, I get 2. So all of that works out to be 2. So I have 30 times 2 times d theta over dt equals 3. So d theta over dt is equal to 3 over 60, which is 1 over 20. And what would my units be then? It's radians per second. Does that make sense? So if we don't have anything, we put radians. So it's like nothing per second, radians per second. And how can you figure that out? You could go back to your original and you could say, okay, what was this 30? This 30 was 30 meters, right? Tangent of theta is a number, and y is a meters. So when I took the derivative, this was still 30 meters. This was a number. We don't know what this is, but we know that dy over dt was meters per second. So if you take meters per second and you divide over by meters, you end up with just 1 over seconds, right? So when that happens, when you have 1 over second, that's really radians. Radians is the non-measure, okay? So you can write radians in then. Do you guys understand what I'm talking about? See lots of scared faces. If you're scared now, oh man, we're getting ready to do a trapezoidal trough. All right, let's do this construction worker one. So a construction worker pulls a 5-meter plank up the side of the building by means of a rope tied to one end of the plank. Okay, the worker pulls the rope up, so this distance right here that I drew in blue is increasing. It's getting bigger by 0.15 meters every single second. Do you guys see that? As that happens, this part I'm drawing in green down at the bottom, the part in green gets smaller, right, every second, okay? So what we're going to use is we're going to use the Pythagorean theorem. So I'm going to have x and I'm going to have y, and then 5 is a constant. So I can do x squared plus y squared equals 5 squared. And I can take the derivative. So I have 2x dx over dt plus 2y dy over dt equals the derivative of 25 is just 0. And I told you whenever I do Pythagorean theorem, I always get rid of those 2's. I just divide out by 2. It's like I divided the 0 by 2. All right, so it says, how fast is the end of the plank sliding along the ground? So we want to find dx over dt when x is equal to 2.5. So we know x is 2.5. We know we're trying to find dx over dt. We don't know y. So that's where we draw our second triangle. And we're like, okay, well, I know at this point in time, x is 2.5. This is a 5-meter plank, and I want to find y. So we do Pythagorean theorem. You guys agree? So I do 25, right? 5 squared minus 2.5 squared is 6.25. So I get the square root of 18.75, which is like 4.330 and something. So I'm going to store as a, just in case I need it. So I'm going to put a in, and then I have dy over dt equals 0, and now I solve for dy over dt. Oh wait, dy over dt we know, don't we? Yeah, thank you. Dy over dt is the 0.15. So I'm going to do a times 0.15, subtract it over, divide by 2.5. So dx over dt is going to be negative 0.2598 something, so negative 0.260. So negative 0.260 meters per second. You get it? 2 times x. Oh, I took out the 2's. I divided by 2. You can divide by 2. Like, you can leave your 2's in there if you want. Yeah, you should get the same. So did you store your y value when you found y? I don't know. Try it again. Maybe just put it in the calculator off. I think that's right. Did you guys get the same thing? Okay. I remember that number, I thought. All right, so it says how fast is the end of the plank sliding along the ground? So the end of the plank is getting closer to the building at a rate of 0.260 meters per second, right? So kind of be careful with those negatives. So maybe write a final statement for each thing, okay? Right, are you still perplexed?
So should that be a positive 0.260?
I would say write a final sentence. So like I would say something like the plank gets closer to the building at a rate of 0.260 meters per second. So that way you definitely have it, right? All right, so number 4. So gravel is being dumped from a conveyor belt at a rate of 30 cubic feet per minute. So that's our dV over dt. And so it's going up this conveyor belt and it's getting like dropped into a cone shape. And this cone shape, the diameter and the height are expanding at the same rate, which I think doesn't really happen. I think gravity would make the diameter grow faster than the height, but you know, what do I know? I didn't write this calculus book here, this problem at least. I did write the rest of the book, but I used this problem from somewhere. All right, so its coarseness is such that it forms in a pile in the shape of a cone whose base diameter is equal to the height. So how fast is the height of the pile increasing when the pile is 10 feet high? Okay, so we're going to set up our volume equation. Do you guys all have the volume equations down? Nope, that is a sphere.
I'm really gonna try.
I was telling the other class that I should do derivatives drill, but only with, instead of doing derivatives, they should be geometry formulas that you should know. Yeah, I should do it. All right, so I have 1/3 pi r squared h. And in these problems, the cone problems, I told you that you should always like try to get them in terms of like v equals one variable over here, like either r or h, okay? So in this case, we know that 2r is equal to h. And what we're trying to find is how fast is the height of the pile increasing when the pile is 10 feet high. So we want dh over dt when h is equal to 10. So we should probably get it all in terms of h, right? So let's replace the r with h over 2. So I'm going to have v equals 1/3 pi h over 2 squared times h. So if I hadn't said something about the coarseness of the gravel is such that these are equal, then you can't do this. You have to keep it as r and h in that case. But for the inverted cones, you guys remember the funnel ones? You can always change it, so it's either just r or just h, okay? So upright cones, you can't always do that. Inverted cones, you can. All right, so I'm going to get 1/3 pi h squared over 4 times h, which makes pi over 12 h cubed. So then we take the derivative, so we get the pi over 12, and we have our 3h squared dh over dt. So you can make that pi over 4h squared if you want. And we just plug things in, right? So we know h is 10. And we're finding dh over dt, and we know the volume is increasing, so it's positive 30. So it's 6 over 5 pi, which is approximately 0.382 feet per minute, if you found the decimal. Okay, makes sense? All right, trapezoidal trough, you ready? All right, so I will admit, when I first started teaching calculus, I messed up the trapezoidal trough. So sad. All right, so what I was thinking is, oh wait, we use similar triangles, so we should use similar trapezoids. But remember, so don't draw this, but similar triangles, we know our r and our h are in the same ratio as this r and this h, right? The little r's, okay? Why can I not do that? So like for the water, this was the water. Why can I not do that for a trapezoid with water in it? Yeah, Grant?
I have actually proportion.
What do you mean it's not proportion? Why is it not? Is their height in the same ratio as the height as top to here? Maybe. They probably are. What about this? Break it into its two trapezoids, the blue one and the other one. They have exactly the same base. Do you guys see that? So they can't be similar. It's the same measurement on the bottom. Do we see that? Okay, so they cannot be similar. So when we're doing these similar trapezoids, what we're going to do every single time is we're going to take this trapezoid and we're going to use similar triangles right there. So we're going to create a little X and we're going to use that. Okay, so you probably want to write kind of tiny. If you need an extra piece of paper, you can use an extra piece of paper. Okay, so here we go. Are we ready?
We're ready. Let's go.
Let's do it.
Dive right into
All right, so the cross section of a 5-meter trough. So when I say 5 meters, this is 5 meters from here to here. Is the bottom of that trapezoidal trough, is it the same as the bottom of the water? Yes. Is it always the same? Right. So that's constant.
Our human calculator is gone.
All right, and then we have a 2-meter lower base. So this is 2 meters. Is that constant? Is it the same as the water? Yeah, that's constant. A 3-meter upper base. That is not constant. You guys see as the water, here's the water one. It's not the same. Julie, are you with me? Okay, so then water is running into the trough at a rate of 1 cubic meter per minute. So dv over dt is equal to 1. And we want to know how fast is the water level rising, so find dh over dt when the water, so when h is 1. Okay? So this is going to be my h. So for the whole thing, this would be the h, but for just the water, it's going to be right there. So it gets a little confusing because we always talk about the trapezoid of the water and then the trapezoid for the whole shape. All right, so my volume formula is the area of the base times the height. The base of this are these two parallel bases, which are trapezoids. So we know when we do the area of the base times the height, then my area of my base is a trapezoid. So it's 1/2 h times b1 plus b2. Do we all remember that from geometry? Trapezoids? You better, because we're going to use lots of trapezoids in calculus. All right, so I'm going to have 1/2 h times b1 plus b2. And then I don't want to use h again because h is going to be something different. So I'm going to use an L, not for slant height or anything like that in geometry, but for the length of this. So that's going to be my length. Okay, so b2 is constant. That's the bottom base. b1 changes. So this was my original b1. If it was full, this would be the new b1. Okay? Do you guys see where b1 is? Okay. So b1. And then the height of the water changes. So here's the height if it was totally full. Here's the height of the water now. Okay? So here's what we're going to draw. So the key to doing these problems is if we can get it in a single variable, we're good. So we could start out by plugging in the constants. We're like, okay, well I know b2 is 2. I know my length of the trough is 5, so I at least have that. But you should always be able to draw a sketch so that h and b1 are related as well. So here's the sketch. So off to the side, kind of draw a trapezoid. You probably want it somewhat big so you can sketch on it. So here's our water. We knew the top of this was 3 meters, and the bottom was 2, and we said we were going to use similar triangles. Just because we just don't have enough variables, we put an x here. We just need more variables in this problem. And this is going to be the height of the water. We're going to divide it over here as well. This is also x. What is the distance from here to here? It's 2, right? Do you guys see? So 3, if this was 3, and we had 2 down here, do you guys see how this is like, what should these ones be? So along the top with the 3, this is also 2. So what should this one and this one be? Yep, 1/2, exactly. So we're drawing in everything we know. So this whole distance is what we're referring to b1. So b1 is equal to 2 plus 2x. And we also know from the similar triangles that 0.5 over x is equal to 0.5 over x is equal to, what was the height of this whole thing? Did I write that down? I didn't. 2. Okay, so it's equal to 2 over h. So we're going to try to get everything in terms of h. We're going to try to take this b1 and write it in terms of h. So let's start with our similar triangles. 0.5h is equal to 2x. So h is the same as so 2 divided by 0.5. Hang on. Divided by 0.5, so 4x. I don't know if that's what I want, though. Hang on, is that what I want? No, I want x. I want to solve for x. So x is equal to 0.25h. Because now I go here. It's like multiple substitutions. So I say, okay, I have b1 plus or equals 2 plus 2 times 0.25h. So it's going to be 2 plus 0.5h. And now we plug that in there. So now we get V equals 1/2 h. B1 is 2 plus 0.5 h plus 2, and then times 5. So we get V equals 1/2. Let me write that as 5 over 2h. I'm going to get annoyed with that 5 at the end. So 5 over 2h times 4 plus 0.5h. So we get 20 over 2 is 10h plus 0.5 is 1/2. 1/2 times 5 over 2 is 5 over 4h squared. Okay, so look at what we started with. A crazy formula that had V, H, B1, B2, and L. Imagine all the crazy math teachers that make you start from there, and they make you actually take the derivative of that. Think how messy that will be. And then say, thank you, Mrs. Cox, for showing me this other way.
Thank you, Mrs. Cox.
I know it's still complicated, but it's better than the alternative. So you guys can handle this. So now we take the derivative, dv over dt is equal to 10 dh over dt plus 5 over 2 when I take the derivative h, dh over dt. And we plug in, we knew what? dh over dt was 1, I believe. Is that right? No, that's what we're trying to find. H is 1. I did 5 over 4 times 2. So I'm going to plug in h equals 1 and dv over dt is 1. So I get 1 equals 10 dh over dt plus 5 over 2 times 1 times dh over dt. So I have 10 of something plus 2.5 of something. So I get 12.5, right? So 12.5 dh over dt is equal to 1. So I get dh over dt is 1 over 12.5, which is 12.5 was 25 over 2, so it's going to be the reciprocal, which is 2 over 25. Or you could have a 0.4. That's right, 400ths, 0.04.
You're subtracting 1 from 12.5.
No, I was dividing the 12.5 over here. 1 divided by 12.5. So what is this, meters per, what was it minutes?
Oh, okay.
Yeah, minutes. That's our answer. Okay, you can have one like that on your homework. If I put
We could do this one. So water is leaking out of an inverted conical tank at a rate of 6,000 centimeters cubed per minute. At the same time, the water is being pumped into the conical tank at a constant rate. The tank, so it's an inverted cone, right? The tank has a height of 600 centimeters. And the diameter, oh, I always draw these wrong, is also 600 centimeters. I should have looked first. If the water level is rising at a rate of 29 centimeters per minute, so dH over dt equals 29, when the height of the water is 150 centimeters, find the rate at which the water is being pumped into the tank, so the dV over t. So when h equals 150 centimeters, find dV over dt. Well, yeah, it's really the rate at which the water is being pumped into the tank. It's also being pumped out of the tank, right? So our dV over dt involves the rate in and then minus the rate out. Or if your rate out is negative, I guess plus the rate out. What should I say? I'll say plus rate out, but I'll say it's negative. It's kind of tricky. So we're not going to worry about this 6,000 till the very end, because that's how much it's leaking out right now. But I want to find the total change in the volume first, okay? So I'm going to have V equals 1/3 area of the base pi r squared times h. So as the water is draining, you guys do have similar triangles. So you have the radius of the water and the height of the water is in the proportion 300 to 600, right? So radius over height equals 300 over 600. In other words, radius over height equals 1/2. So 2r equals h. So we want the height, right? The water level is rising at a rate of 29 centimeters per minute when the height is 150. Sometimes you have both things, and then you kind of have to play with it like after you're plugging things in. Remember how you can always take the derivative here and say 2 dr over dt equals 2 dh over dt if you ever, or equals, not 2, equals dh over dt. So you could always do that if you weren't given like all the h's or all the r's. So we have pi, r is h over 2. So we end up getting 1/3 pi h squared over 4 times h. So pi over 12 h cubed. Cubed is looking weird. So now we can take the derivative. So I get dv over dt equals pi over, it will be 4 h squared dh over dt. And I plug everything in. So I know h is 150 centimeters. dh over dt is 29. dv over dt is what I'm trying to find. I'm just going to find it all as a decimal. Well, it would be 163,125 pi. But as a decimal, it would be 512,472.302. Lots of twos. All right, so the last thing that we have to do is we have to say, oh, but this was the total rate of change, sorry, of the volume. And we have water coming in and water coming out, right? So water is leaking out at a rate of -6,000. So that means that water has to be coming in even faster than this number that we have. Do you guys understand what I'm saying? To kind of offset that rate out. So the rate n minus 6,000 has to equal that total change in volume. So you just add 6,000 over. So it should be 518,472.302 centimeters cubed per minute. So treat it as a total rate of change of the volume, and then at the end adjust. Okay, does that make sense? All right, one more type of problem. It's actually two, but I think I'll just do one. All right, so do you want me to go back? So shadow problems. So shadow problems are in every single book, they're probably on every AP test. I'm sure in the multiple choice they'll have some shadow problems. They're kind of weird. They're easy, but they're weird, like thinking about it. Okay. So it says Audrey is 5 feet 6 inches tall and walks at a rate of 4 feet per second away from a light that is 15 feet above the ground. Okay, so we have some kind of light post. And this light is shining down. And she's standing or walking, and she has some kind of shadow that's being formed. So when she is 10 feet from the base of the light, part A, find out what rate is the length of her shadow changing. So I'm going to make S for shadow. My students in the past have told me to do cursive S because my S's look like 5s most of the time. So we'll do cursive S. So it's saying she's walking at a rate of 4 feet per second away. That means this distance right here is changing. She is gaining 4 feet every single second. Okay, I'm going to call that X. Yes, very. She's running. Speed walking. All right, so we want to figure out how to write a proportion using this. We do have similar triangles. Do you guys see we have the height to height? What was her height? 5'6", so I'm going to write 5.5, right? 5.5 feet. So we definitely have 15 over 5.5. But then this total length, we have to write as X plus S. So we have X plus S over S. Do you guys see that in the similar triangles? Height over height equals base over base. So we can multiply and simplify before we take the derivative because we don't want to take the derivative now. It looks gross, right? So you can always rearrange and distribute and subtract. So subtract the 5.5s over. So we get 9.5s equals 5.5x. And you could even, do something with the numbers. You could like divide the 5.5 over or whatever. Yeah.
Could you like use the fact that x plus s equals 10 to do anything?
Not yet. Okay, because she's walking away, so it's getting bigger. All right, so you can take the derivative at this point, which is pretty easy. It's just saying that 9.5 ds over dt equals 5.5 dx over dt. Which means that these are what we call directly related. Okay, we talked about direct relations in Algebra 2. It was always y equals k times x, right? So I could divide the 9.5 over, and I'd have a rate equals some constant times the other rate, okay? So what this means is the rate that she's walking directly affects the rate that her shadow is changing, which totally makes sense. Do you guys get it? So the faster she walks away, the faster her shadow changes, okay? So basically, it doesn't matter how far she is from the base of the light. That's what throws people off. That 10, completely useless. We never have to plug that in. Okay, it doesn't matter how far she is. The thing that does matter in the real world, right, with physics, is if she's like 1 mile away from that light, is she really casting a shadow from that light? Not really, because that light is kind of dispersed, right? Does that make sense? But really, it doesn't matter how far she is. If in true, like, if the light was shining forever, like the sun, right? It doesn't matter. So it's kind of strange. That's what's confusing for students when they do this, because they want to put that 10 in somewhere, and you don't actually need it. So it says at what rate is the length of her shadow changing? So the length of her shadow is this ds over dt. So 9.5 ds over dt equals 5.5 times 4. She's walking away at a rate of 4 feet per second. So when I divide it out, I get ds over dt equals 2.316 feet per second. So that's part A. Now part B is very simple. It's phrased a little bit differently though, and this is what's a little bit confusing, because for part A it says at what rate is the length of her shadow changing. Do you guys see, like on the ground, that's the length of her shadow. That's the S, right? But at what rate is the tip of her shadow moving? The tip of her shadow is a little bit different. The tip of her shadow involves how fast she's walking and how fast the shadow is changing. Do you guys see? The tip of her shadow is actually the x plus s, because it's that distance right there. How fast is that point moving? Do you guys see what I'm saying? Okay. So the tip of her shadow is going to be dx over dt plus ds over dt. Right? So maybe I should say tip equals x plus s. So when you take the derivative, the rate of change of the tip of the shadow, it equals that. So dx over dt was the 4, and then 2.316 was what we found. So we get 6.316 feet per second. Okay, so her shadow is changing in size, but she's also walking or running or whatever. So that's moving the tip of the shadow as well. Yes, do you get it? It's kind of weird. That's what people don't like about these. All right, and the last type of question we have involves some trig again. So it says a sandbag is dropped from a balloon at a height of 60 meters when the angle of elevation to the sun is 30 degrees. Find the rate at which the shadow of the sandbag is traveling along the ground when the sandbag is at a height of 35 meters. Okay, so I don't know if you guys have, if you guys can visualize this or not. I need like a video of this. So as this drops, okay, its shadow is right here to begin with. Yeah?
Please don't take umbrage to my remarks, but this may be the single least applicable problem I've ever encountered in all my years of taking that course.
Okay, you guys, have you guys ever seen this as you drop something, the shadow moves along the ground? Do you not understand what I'm saying?
I
That's
know
fine.
that a lot of people say I'll never use this in real life, but they have to. But this seems a tad.
I don't know. It's a related rates problem.
Perhaps inconsequential.
All right, here we go. So find the rate at which the shadow is traveling along the ground when the sandbag is at a height of 35 meters. So what's going to happen is as the sandbag drops, the shadow is going to zoom over here, and it's going to end up being directly below it. Does that make sense? Do you guys understand that?
Wait, is it directly below it when it's on the ground?
As it's falling, yeah, as it's falling, it's going to go to directly below it. Yeah. So how do we do this? Okay, the rate that the sandbag is dropping, I gave that to you. So I gave you the position. So the position of the sandbag is this. That's, you know, the original height minus gravity. Gravity times t squared. Okay, so as we set this up, right, that's going to be its position. We'll call that y. Or I guess I called it s in the problem, so we'll call it s. All right, we have our 30 degrees, and our shadow's path is also changing. We'll call that x. But our 30 degrees never changes, right? It just is becoming a smaller triangle, and so on. Okay, so our 30 degrees is constant. So we're going to have opposite over adjacent. So we're going to say tangent of 30 equals opposite over adjacent. But that s ends up involving the 60 minus 4.9 t squared. That's what it is. So I'm going to have tangent of 30 times x, and then times all that. And now I can take the derivative. But the nice thing about this is when I take the derivative of a t, it's dt over dt. So I'm not going to need that there, right? Does that make sense? So as I take the derivative, I'm going to have tangent of 30, which is a number, times dx over dt equals negative 9.8t, and then dt over dt is just what it is. It's 1, right? And we can solve it out. So we want to know when the height is 35 meters. Well, we can find out 35 equals 60 minus 4.9 t squared. We can solve for t and then plug that in here. And then the dx over dt is what we're solving. So we get our t, we plug it in here, and then we finish it out. Okay.